behavior at zeros. So here's the first one. So when the curve is just passing through, so like this, you will have multiplicity of 1 for your equation. So that's the word used, multiplicity, 1 here, because you're just passing through. Okay, so same thing when you have something like this. This one is the increasing part. The other one is the decreasing part. So when the line is just passing through like that, and you will have a multiplicity of 1 there for the 0. So remember, 0 means um, x-intercept. Then you can call that as root also from the previous sections. Okay, so that's the first behavior, just passing through, multiplicity of 1. And then when it's like a parabola, it touches the x-axis and then touches the x-axis and then bounce back. So it's like a parabola. So this is multiplicity of 2. Multiplicity of 2. Again, the word multiplicity is used here to describe the behavior of the 0. So again, it's like a parabola, and this parabola is opening upward. So it means your A here, it's positive. Here is A is equal to negative. So the parabola is opening downward. Okay. If you have a parabola equation, so if you have ax minus h plus k, so this is the standard equation of the parabola. A is the number beside that term, x minus h power of 2. So that's our A there. The third behavior is when it touches the x-axis and then it wiggles downward. So it's a cubic curve. You've seen this in the previous section also. So that would be multiplicity of 3, because that's the behavior of the curve at that 0. So the intersection point is at the 0 there. And it's a cubic curve, so multiplicity of 3. So it means you have a power of 3 there. So that's the word multiplicity means also. Okay, so those are the 3 just passing through. That's multiplicity of 1. It touches the x-axis and bounce back like a parabola. Multiplicity of 2. And then the last one, it's like a cubic curve, multiplicity of 3. Now we can see some of the examples in few minutes by looking at our graphing calculator, and let's plug in some equations there. So next would be the turning points. So turning points and end behavior. So there's always an end behavior also when we look at the graph. So if you have the parabola, the turning point is just 1, so it turns here and go back. So but the end behavior, as you can see, it's pointing upward for the parabola if A is positive. If A is negative, then the parabola is facing downward. And you still have one turning point here, the vertex and the end behavior of the curve. So it says end behavior and turning points would be pointing downward. And there is a formula for the turning points also, and that's n minus 1. Okay, so it makes sense because when you have a parabola, that's power of 2, n minus 1, so n is 2 there, 2 minus 1 is 1, so you have only one turning point for a parabola, which is the vertex. So here's the turning points. A polynomial function of the degree n has at most n minus 1 turning points. So this is the formula to find the turning points. So when you have a parabola, n would be equal to 2 for parabola. And then the number of turning points would be only 1 because that's n minus 1. So you will get one turning point, which is the vertex. So you can see from the previous example, you have a parabola like this. The vertex is at the bottom of the parabola, and you have only one turning point. So A here is positive, and when the parabola is pointing downward, A is negative, and you have only one turning point also, which is the vertex. In this case, the vertex is the highest point of the parabola. So that's the vertex. Okay, so that's the turning points and the end behavior. So we can play around and look at those. So if you have a power of 3, that's a cubic curve. So cubic curve is here. It's like an inverted S. It's like something like that for a cubic curve. Now, as you can see, the turning point is over here. So uh, power of 3, let's say y is equal to x power of 3. And if you're looking at the formula, which is n minus 1, so you can put 3 minus 1, so you will have 2 turning points. So, which is actually true. Okay, so as you can see, I'm going to show that to you. This is the first turning point. It's going downward from the point of origin. So, and the other one is over here. From the point of origin is going upward, curving upward. So you have two turning points. Now the end behavior of the curve, as you can see, one is pointing up and the other one is pointing down. So that's the end behavior of the cubic curve. Okay, and remember, when your A here is positive, so if that is a negative, it will flip the curve. So that would be on the other side. It looks like this one is going like this for the cubic curve. If your A here is negative, A is equal to negative. If your A here on the first one is positive, so that's why you have that curve. So I'll just put a different color, positive there. For the purple one, it's a negative, and the red one, it's a positive for A. A is the number beside your term x cubed, so your A should be here. A is here. Okay, that's beside x cubed. Okay, so let's look at the graph. Let's change our screen and see the different turning points in behavior and the behavior of the curve or the behavior at zeros. Okay, so let's go to our graphing calculator. Okay, so we have here in Dismus calculator. So what we're saying a while ago, when you have like y is equal to, let's say, x power of 2, let's put minus 2 here. So the parabola will be 2 units down. So you can see the zeros here. So the first zero is here and the second zero is here. And remember, this is just passing through. So the multiplicity of 1. So you have 2 zeros. So the highest power you've seen in the equation is power of 2. So you have the match 2 zeros. That means you have a power of 2. And if I'm going to play with the sign, remember this is positive, so it's opening upward. So the end behavior of the curve would be going up. So put a minus, it's flipping downward. And as you can see there, there's no more zeros. There's no more x-intercepts. Remember, zeros are x-intercepts. So at this point, there's no more zero. If you want to translate this plus 2 up, then you will have 0 again. 1 0 here, another 0 here. Now, if I'm going to play with the power of 3, for example, I cube, so that is the cubic curve. You can see the end behavior here is going downward and the end behavior is going upward. Looking at the turning points here, it's 1 and 2. So that's 3 minus 1, that would be 2 turning points. In the previous presentation, parabola has only one turning point. That is the vertex. I play around with the sign. If I put minus, it flips. And you can see that the curve now, it's on the second quadrant instead of the first quadrant. And the other curve pointing down is on the fourth quadrant instead of the third quadrant. And these are family of curves. So if I go power of 5, still a cubic curve. As you can see that, power of 7, still a cubic curve. So if I'm going to play around with parabola, and then I will say power of 4, that is still a parabola. Power of 6, that is still a parabola. Okay? So once you will play around with this graphing calculator, you will understand more about uh, the curve and the graph and about the behavior at zeros and the endpoints and the turning points. So we're going to put an example here. Let's have power of 3 and see what would be the behavior here at zeros. So okay, so here's the zeros here. So we have the highest power, or the degree of this equation is 3, because the highest power is 3. So we're supposed to have 3 zeros. 1, 2, 3. They are all passing through. So multiplicity of 1. So again, you have 1, 2, 3. So you have 3 zeros and it's just passing through. So it means multiplicity of 1. So let's try with multiplicity of 3 and 2. So let's try that one. Another example. And power of 5. Put the x power of 5 plus 4 x power of 4 plus x cubed minus 10x power 2 minus 4x. Now I want you to look at the graph here and see the difference between the previous graph. So here's the 0. Now looking at this 0 here, negative 2, it's a cubic curve. So it means this one is multiplicity of 3. So it touches here and then to the x-axis and wiggles down. The other one here, it touches the x-axis but bounce back like a parabola. So the one here, it's multiplicity of 2. So you have 2 zeros here, you have 3. So 2 plus 3, that's how we get 5 here. That matches the number of zeros. So 5 is the degree of the equation, and that is our n. That's the highest number or power that you can see on the terms there, and that's 5. So that means we have 5 zeros on the graph. So 3 on in here, because this is a cubic curve, multiplicity of 3, and 2 here as a parabola. So total of 5. So you can see also the end behavior of the curve. It's going downward. The other part is going upward. Okay. And if you're going to apply the turning points formula, which is n minus 1, so you will say how many turning points you're going to have. So that's 5 minus 1, so that should be 4 turning points. So we can actually try that. Let's see how many turning points we have. We have 1 over here, and 2, and 3 here. When it goes down, right? 3 turning points. And then 4th. This is the 4th turning point. So total of 4 turning points. So that's 5 minus 1. So applying that formula also. So most of our problems here can be analyzed using a graph. So play around with the graph and then see the different behavior of the curves and try to match that with the number of zeros and the degree of the equation. So this is the behavior at zeros.